Good morning, dear student. In today's lecture, we will discuss the next important point of our catalysis, that is the importance of homogeneous catalysis in synthesis of high value of chemicals. So it is also the importance of homogeneous catalysis in synthesis of high value of chemicals. So why homogeneous catalysis or homogeneous catalysts are important? So we already discuss the distinguishing features between homogeneous and heterogeneous catalysis. So again, if you consider this homogeneous catalyst or homogeneous catalysis, we know that the important characteristics of this homogeneous catalysis is that its selectivity, that is, the homogeneous catalysts are very selective. So the product which we want, we get in desired amount is nothing but the selectivity of the catalyst. So they have very high selectivity, therefore they are important in any chemical reaction to get a desired product. So selectivity is very important. Second, that is the reaction mechanism is well understood. So what are the steps which is involved in this catalytic cycle by using homogeneous catalysis? The mechanism is easy to understand, therefore it is very important. So we understand which reaction is going on in this catalytic cycle, either oxidative addition, reductive elimination, insertion, beta hydride elimination reaction. But in heterogeneous catalysis, the reaction mechanism is very difficult to understand. So therefore they are important in any chemical reaction to convert the reactant into the product. So selectivity, reaction mechanism. Then another important point is that they require low temperature and pressure. So the temperature and pressure which is required to convert whatever the substrate or reactant into the product is very low, okay, in presence of this homogeneous catalysis. So in presence of homogeneous catalysis, low temperature and pressure is required. So you can easily maintain the temperature and pressure in your laboratory to convert the reactant into a desired product. Again, the solubility, next important is solubility. They are soluble in reaction mixture. That is, the substrate or the reactant and the catalyst, that is homogeneous catalyst, are in the same phase, solubility. So they are soluble in reaction mixture. It is also the important characteristics of this homogeneous catalysis, therefore they are important. Another important characteristic is that in exothermic reaction, they dump the heat which is generated in exothermic reaction, or they dump the heat into solution. If exothermic reaction is going on and lot of heat is removed, then the heat is dumped into the solution, that is into the reaction mixture. So these are the important characteristics of this homogeneous catalysis, and therefore they are very much important in any reaction, organic synthesis reaction, because they are highly selective. Reaction mechanism is well understood. Low temperature and pressure is required. The solubility, they are in same phase, and in exothermic reaction they dump the heat into the reaction mixture. So let us see one by one which organometallic complexes are used as a homogeneous catalysis. So let us see one by one. So which is the inorganometallic complexes which is used as homogeneous catalysis. The first one is very important. So, first we will discuss the reaction, that is the cycle for hydrogenation of alkene. Hydrogenation of alkene. So, we will discuss the catalytic cycle for hydrogenation of alkene using the catalyst, that is rhodium chloride triphenyl phosphine. This catalytic cycle, that is hydrogenation of alkene, it is also known as Tolman catalytic cycle. Tolman catalytic cycle. So, it is very important. Many times it is asked in examination, explain the catalytic cycle for, explain the Tolman catalytic cycle for hydrogenation of alkenes. So, hydrogenation of alkene or Tolman catalytic cycle is one and same. Hydrogenation of alkene with the help of rhodium chloride triphenyl phosphine, it is also known as Tolman catalytic cycles. So, let us see Tolman catalytic cycle or hydrogenation of alkenes with the help of this rhodium chloride triphenyl phosphine. So, in this hydrogenation of alkene, there is a two type of mechanism are involved. Two type of mechanism are involved. Two type of mechanisms are involved. The first mechanism we will discuss, which is, we are very much familiar with the first mechanism. So, let us see the mechanism first for this hydrogenation of alkene. So, the cycle for hydrogenation of alkene, it is also known as Tolman catalytic cycle. The first mechanism we will discuss, that is, if you consider the complex mechanism first, then we consider a complex, that is rhodium chloride triphenyl phosphine, PPS3. So, this is your Wilkinson catalyst for hydrogenation of alkenes. So, the first step, so we can write here mechanism first, we can write here. So, rhodium chloride triphenyl phosphine. So, it is a 16 electron species in which rhodium is in +1 oxidation state, which undergo oxidative addition reaction with H2. Oxidative addition reaction in mechanism first, this rhodium chloride triphenyl phosphine Wilkinson catalyst undergo oxidative addition reaction with H2. So, H2 is your non-polar species. So, we get here a cis product, that is rhodium, hydrogen is here, then PPS3 thrice, then this PPS3 thrice, here another Cl, here PPS3. So, the 16 electron species is converted into 18 electron species, and the oxidation state, it is increases by 2 units. So, it is in +3. So, the first step in mechanism first is oxidative addition. Second, the 18 electron species, so there is a no sigma donor ligand, there is a sigma donor ligand, but there is a no carbonyl ligand. So, there is no chances of 1-1 insertion or 1-1 insertion reaction. So, 18 electron species, we know that 18 electron species undergo dissociative type of mechanism. So, in this case, there is a dissociation of one phosphine ligand PPS3 thrice, that is dissociation. The second step is dissociation. Second step is dissociation. So RH, H, H, PPS3 thrice, PPS3 thrice, here Cl, and there is a one vacant site. Again 18 electron complex is converted into 16 electron complex. 18 electron complex is converted into 16 electron complex. The next step of this catalytic cycle is that the 16 electron complex with vacant site, it will coordinate with alkenes, that is carbon carbon a double bond. So coordination of alkenes. So here we get rhodium H, H, here PPS3 thrice, PPS3 thrice, here Cl, and here the carbon carbon double bond get attached. That is the coordination of olefins to the metal center. So this is the important steps. First is oxidative addition, second dissociation of phosphine, third coordination of olefins to the metal atom. Again it is converted into 18 electron species. So we know that whenever there is a sigma donor ligand and olefins, that is carbon carbon double bonds, are attached to the metal atom, then there is a chances of 1-2 insertion reaction. So these undergo 1-2 insertion reaction, 1-2 insertion. So 1-2 insertion, after 1-2 insertion what do you get? A rhodium, here you get here H with one vacant site, here PPS3 thrice, here we get CS2 CS3, CS2 CS3, here Cl, here PPS3, PPS3 sites. So 1-2 insertion. So one of the hydrogen is shift here. Okay. So hepticity is decreases by 1 unit. So olefins hepticity, it has 2 hepticity. Both carbon atoms are attached to the metal atom, but in this case only one carbon atom is attached to this metal atom. So this is 1-2 insertion. Okay. Again it is an 18 electron species. Then another, there is a vacant site. There is a vacant site. So we will discuss another, there is a vacant site, and this 16 electron species, 16 electron species, one of the phosphine ligands are attached to this complex, 16 electron complex, and we get here rhodium H, here PPS3 thrice, here PPS3 thrice, here Cl, here CS2, so we can write PPS3 thrice, CS2, CS3, and one PPS3 is there. One PPS3 is there, and finally the last step, that is it is an 18 electron species, it undergo reductive elimination reaction. So it undergo reductive elimination reaction to gives CS3 plus rhodium chloride triphenyl phosphine. So PPS3 thrice, PPS3 thrice. Again we regenerate the original catalyst, that is rhodium chloride triphenyl phosphine. So these are the this is the catalytic cycle for hydrogenation of alkene. It is also known as Tolman catalytic cycle, in which the first step is oxidative addition. Second, we will discuss one step, it is first step is oxidative addition, second step that is dissociation of phosphine ligand, then coordination of olefins, then 1,2 insertion, and then coordination of phosphine, then reductive elimination. So let us see one by one. So which steps we discuss in this catalytic cycle. So this is the first catalytic cycle. So which steps we perform in this catalytic cycle? First, that is oxidative addition of H2. So in mechanism first, so what are the steps? First step is oxidative addition of H2 to catalyst. Oxidative addition of H2 to catalyst. Second, the dissociation of PPH3 ligand, phosphine ligand. So first step is oxidative addition. Second, dissociation of phosphine ligand. Third, that is coordination of olefins. Coordination of olefins, that is carbon-carbon double bond. Then 1,2 insertion. Then 1,2 insertion. The next step after 1,2 insertion, that is coordination, that is bonding of PPH3 thrice, and last step, that is reductive elimination. So these are the steps in mechanism first, that is oxidative addition, dissociation of phosphine ligand, coordination to olefins, then 1,2 insertion, then bonding with phosphine, and then reductive eliminations. So in this mechanism, the first step, that is oxidative addition of H2 to the catalyst, is the rate determining step. It is a slow steps. So why it is slow steps? Because the complex, that is rhodium chloride triphenyl phosphine, the phosphine is strong pi acceptor ligand and they are bulky ligands. So there is a steric hindrance. So the rate of oxidative addition is very slow in the first step. Therefore, it is a rate determining step in mechanism first. So this is regarding to the mechanism first for hydrogenation of alkene. Okay, let us see the second type of mechanism, that is mechanism 2 for hydrogenation of alkenes. Mechanism second for hydrogenation of alkenes. So in mechanism second, okay, let us see once again. A rhodium complex is there, a rhodium chloride, PPH3 thrice, PPH3 thrice, PPH3 thrice. Okay, so we know that these are pi acceptor ligands. So phosphines are pi acceptor ligand, they are bulky ligands. So there is a steric hindrance, and they are, due to steric hindrance, they are slightly unstable. So they are tried to stable by dissociating one of the phosphine ligand. So the first step in mechanism second is the dissociation of phosphine ligand. So after dissociation of phosphine ligand, the vacant site which is generated, it is occupied by the solvent molecule. That is rhodium, Cl, PPH3 thrice. Here all of the phosphine is replaced by the solvent, and this is your PPH3 thrice. Okay, so this is the first step, that is the dissociation of one phosphine. So why there is a dissociation of one phosphine? Because they are bulky ligand. Due to steric hindrance, the molecule or the complex is slightly unstable. So for stability, they will dissociate. So they undergo dissociation type of reaction. So minus PPH3 will be lose out, and we get this complex. It is a 16 electron complex. Again, the vacant site which is generated, it is replaced by the solvent molecule, that is S solvent molecule. Then this complex undergo oxidative addition reaction, that is H2. It undergo oxidative addition reaction. So what you get here? Rhodium H. Again it is a non-polar species, so we get a cis oxidative addition. Rhodium HH. Then here PPS3 thrice. Here another PPS3 thrice. Here Cl, and here one of the solvent molecules. So S stands for solvent molecules. Again, the solvent molecules are easily replaced. By the alkenes. That is, the next step is coordination to the olefins. So carbon-carbon double bond get attached to this metal atom. So they can easily replace this solvent molecule. So next is coordination of olefins. So what do you get here? A rhodium H. Okay, second rhodium H. Here PPS3 thrice. Here double bond. Okay, here Cl, and here one of the PPS3 thrice. So this is the next. So in the first step, there is a dissociation of first point ligand to gain the stability. Then whatever the vacant site which is generated, it is replaced by the solvent molecule. Then this complex undergo oxidative addition. So S2, it is a non-polar species, so we get a cis product. It undergo oxidative addition reaction. After oxidative addition reaction, coordination of olefins. So the solvent molecules are easily replaced by the carbon-carbon double bond. Then the next step is that there is a chances of 1,2 insertion reaction. 1,2 insertion reaction, because carbon atom, carbon-carbon double bond, olefins and sigma donor ligand is present. Therefore, there is a chances of 1,2 insertion reaction. So we get rhodium H, one vacant site. Again here PPS3 thrice. Here we get Cl, and here we get PPS3 thrice. We can write here, and we write CS2 CS3. Then the vacant site, it is replaced by again the solvent molecules. The vacant site is replaced by the solvent molecule. The vacant site, finally it is replaced by the solvent molecule. That is RH HS CS2 CS3 Cl PPS3 thrice. Okay, CS2 Cl, here PPS3 thrice. And the last step, that is the reductive elimination. So the two cis ligands. So here we get CS3 plus, what do you get here? A rhodium. Okay, so one PPS3 is there. Here Cl is there. Here one PPS3 there, and here a solvent molecule is there. Again we get a active species which is involved in this catalytic cycle. So this is the difference between mechanism first and mechanism second. So which mechanism is followed for hydrogenation of alkenes, and which mechanism is not followed for hydrogenation of alkenes? So both the mechanisms are followed for hydrogenation of alkenes, but the mechanism second, that is with the help of solvent, and the mechanism second which have a lower energy, or which is more favorable mechanism for hydrogenation of alkenes, Second, After dissociation of first point ligand, the complex undergo oxidative addition reaction. So this is a fast step, no doubt. This is a fast step. Therefore, in this mechanism second, the second step, that is oxidative addition, is not a rate determining step because it is very fast. But in this case, the rate determining step is 1,2 insertion reaction. The rate determining step for this mechanism second is 1,2 insertion reaction. So keep in mind. So mechanism second involve the steps, that is first dissociation of first point ligand, second step, that is oxidative addition of a complex, okay. First dissociation of first point ligand, third oxidative addition, next coordination to olefins, that is replacement by solvent molecule by carbon-carbon double bond. Then there is a 1,2 insertion. Again solvent molecule is coordinated to the metal atom after vacant site generation, 1,2 insertion, and final, that is a reductive elimination. So this is the difference between mechanism 1 and mechanism second. So in mechanism first, oxidative addition is the rate determining step, but in this case, in mechanism second, it is a fast step. Therefore, it is not a rate determining step. While in this reaction, this 1,2 insertion, it is your rate determining steps. That is your slow steps. So both the mechanisms are useful. Both mechanisms are valid for hydrogenation of alkene, but as compared to mechanism first, mechanism second, it is more favorable, or which is less energetic. Therefore, mechanism second is more favorable, less energetic, and more we can say that the mechanism second is more useful as compared to mechanism first, because directly oxidative addition is not possible because the first point ligands are very bulky ligands. So the rate of oxidative addition, direct oxidative addition of rhodium chloride triphenyl phosphine is very difficult. Therefore, they undergo dissociation. So this is the important step, dissociation of first point ligand, and then they undergo oxidative addition, coordination, 1,2 insertion, reductive elimination. So both mechanism is valid, but the mechanism second is more, we can say that the mechanism second is more easily understand or more helpful for this hydrogenation of alkenes. Okay, in first mechanism, the rate determining step is oxidative addition, while in mechanism second, the rate determining step is 1,2 insertion reaction. So hydrogenation of alkene by Wilkinson catalyst, it is known as Tolman catalytic cycles. So you should remember the Tolman word, that is Tolman catalytic cycle. Hydrogenation of alkene, it is also known as Tolman catalytic cycle. This rhodium chloride triphenyl phosphine, it is highly selective for hydrogenation of alkenes, that is it's highly selective. So it will hydrogenate right here. So it will hydrogenate less substituted alkenes. So it is highly selective. Less substituted alkene is hydrogenated by this rhodium chloride triphenyl phosphine. The second important point is that only here less substituted alkenes. Second, only isolated double bond undergo hydrogenation. isolated double bond undergo hydrogenation. So the double bond in conjugation, it is not hydrogenated by rhodium chloride triphenyl phosphine. So let us see the example, that is, so in this reaction, rhodium chloride triphenyl phosphine, so it will reduces, or it will convert this double bond into single bond. So this carbon carbon double bond get hydrogenated. This carbon carbon double bond does not hydrogenated because it is in conjugation. So rhodium chloride triphenyl phosphine, it is very selective. It only hydrogenate isolated double bonds. The double bond which is not in conjugation. The double bond which is not in conjugation. Another important characteristics of this rhodium chloride triphenyl phosphine is that it is used for decarbonylation reaction. Decarbonylation, carbonylation reaction. Decarbonylation reaction. For example, R C double bond OH. So in presence of rhodium chloride triphenyl phosphine, so we get here RH plus Cu. So decarbonylation of Cu. So these are the important points regarding to the rhodium chloride triphenyl phosphine. We will discuss mechanism first, mechanism second. So mechanism second is less energetic and it is more easily understood or more easily follow for this hydrogenation of alkene. The hydrogenation of alkene with the help of Wilkinson catalyst, it is also known as Tolman catalytic cycle. This catalyst is very selective. It will hydrogenate only less substituted alkene. It will hydrogenate only isolated double bond, that is double bond is not in conjugation. So only isolated double bond get hydrogenated, and it is also useful for decarbonylation, that is removal of carbonyl from the substrates. So in next lecture we will discuss the next type of homogeneous catalysis, or next important organometallic complex which is used as a homogeneous catalysis. Thank you.